Hey guys, in this particular video I'll be introducing you to something called relative velocity. So let's get started. Let's say that we've got this arbitrary shaped object just here, and let's say on that arbitrary shaped object we've got a point which I'll call point A. We've also got a point which I'll call point B right here. Right, these holes just are there to help you see the particular points in more clarity. Right, and let's say that purely out of interest at this point we wanted to define the position vector from B to A. So in red, let's draw that. This is the position vector from B to A, and I'll define it to be RA slash B. And the reason why I've written it as A slash B is that's the position vector to A from B. So you can think of it as what A looks like relative to B. Okay, so now that I've defined that, we still really have no idea what this even means. So we'll need to have some understanding of vector algebra to figure that out. So if we create an axis just here, in fact let me zoom in a bit so you can see a little bit more clearly. If we have an axis just here, this will be our x, this will be our y. Remember, we can choose to place our axis wherever we want. Then if we wanted to find out what the position vectors of A is, then we just connect the dots from our origin to our point A. So that'll be the position vector to A. And if we wanted to find out what our position vector to B is, we do the exact same thing. So this will be the position vector to point B. Well, we know using vector algebra now that we can figure out how to describe these vectors in terms of in terms of each other, right? So we know that if we walk up this blue line and down this red line, that'll give us that'll drop us off at the same position as if we were to walk up this green line right here. So we can write that mathematically, saying that the position vector RB plus the displacement vector RAB must be equal to your position vector RA. That's just using a little bit of visual vector algebra right here. You're just noticing that going up this blue path and down this red path drops you off at the same position as if you were to go up this green path. Okay, well that's all well and nice so far. This so far has nothing to do with velocity so far, so let me just get into that real quick. What I'm going to do now is I'm going to differentiate both sides with respect to time, and I'll leave you with the derivative of RB plus the derivative of RAB is going to be equal to the derivative with respect to time of RA. Let me do it in white. Of RA. Okay, so now that we've got that sorted, we can actually use a very interesting formula to simplify this down. Recall in a previous video, I described that the derivative of any position vector or displacement vector with respect to time, I'll just write that as r, will just be equal to its velocity vector. So that just basically means if you've got a position vector to say point C or point D or whatever, that means that if you derive that with respect to time, that's the same thing as finding that velocity at that instant. Okay, so we can use this. In fact, let me put a box around this. This is something I proved in a previous video. We can use this to figure out what was written above. So we can write this as the velocity at point B plus the velocity of A relative to B is going to be equal to the velocity at point A, right? So this is a huge formula right here, and you can write it in this form, that's totally fine, but I find that it's usually easier to write it in this form, just rearranging it a little bit. You can write that as the velocity of A relative to B is going to be equal to the velocity of A minus the velocity of B. And a good way I use to remember this is you look at the A here to the left, and you look at the B right here, and you notice that it's A right here and B right here. That's just a way you can remember this formula. And because I've drawn an arbitrary shaped object here, this is true in all possible cases, right? So this is a fundamental truth about any arbitrary shaped object. So that's the formula down packed. Now, in order to properly understand how to apply this formula, I'm actually going to show you how to apply it to an arbitrary geometry. So let me just insert this clip art just here. In fact, let me just copy this. I'll use the same arbitrary shape. So let's say that we've got this object right here. Okay, and let's say that point B now has a velocity roughly in this direction. Let's just say this velocity right here is the velocity at point B at some instant, right? And let's say that we've also got the velocity at point A, say roughly along this path, and this will be the velocity of point A, right? There are a range of different velocities that these points can have at a particular instant. I'm just choosing these two as arbitrary velocities. Okay, so what I can do now is I can write the velocity of A as equaling to the velocity of A minus the velocity of B plus the velocity of B. And you may be thinking to yourself, well, that's a silly thing to write. Of course the left-hand side equals the right-hand side. These two things cancel out to 0, right? And you're totally right, it does. I should really say the 0 vector, right? They cancel out to the 0 vector, right? But the reason I've done this is so that I can help split this motion, this complicated motion this object will undergo, into both translational movement and rotational movement. So bear with me, I'll show you how to do that. So this particular movement that this object is swinging out at this particular instant is the exact same as, in fact, let me just copy that object over here again. That's the exact same thing as having a velocity VB up here, just unchanged from before, plus the velocity of VA. Actually, let me just do it this way. It's going to be the same as the velocity of B upwards, plus, and let me just paste that object over here again, plus no velocity at point B. So what I'm saying is I can split this movement of this object at this particular point into two types of movement. One is this type, plus no movement here at point B, plus, and let's see what we've got left. It'll have to be VA minus VB. So it'll be plus this movement, VA, that's VA, and then minus VB. I think it looks something like that. That's going to be minus VB. Okay, so that's this movement, this complicated movement in this first left-hand side drawing that I've got just here, can be split into two different types of simultaneous movement. One where you've just got two VB vectors acting at points A and B, and in order to finish off the equation, because you can't just choose to replace this with an arbitrary vector, you have to make it the same, so we know that it has to be VA minus VB on the right-hand side. Okay, so now that we've got that sorted, we'll notice then that because this particular drawing has only VB velocities acting on it at an instantaneous time, that means that this is purely translational movement. I hope this satisfies your intuition. Just imagine point A and point B moving with both VB at this particular direction, this particular magnitude. That just means that this thing's going to be moving like that. It won't be rotating, it'll just be under translational movement. Now let's consider what happens with this particular object. Well, let's try and connect the dots between here and here. What's this particular vector I've made just here? Well, that particular vector, using what I did before, is just going to be VA minus VB, right? That's just following the green lines, following the blue lines, must be equal to the red line, right? But what's VA minus VB? Well, if you look up above, I've written VA relative to B is equal to VA minus VB. This is huge because we can substitute this in for our displacement vector we have just here, right? And the beauty of this is if you were to connect dots from A to B, right, you'll notice that this line, this white dotted line, will be perpendicular to this red line. Now, I haven't proven that in this particular video. In order to prove that, you really need to have a much more involved idea of linear algebra, but I hope by drawing these vectors to scale, you might be able to see that. Okay, so this white dotted line will be perpendicular to this red line. So what does that mean? Well, just recall that if you've got an object right here and you've got another object swinging around it, recall that from circular motion, that means that your velocity right here will be perpendicular to your radius right here. Remember, this is just circular motion. This is from a video I've shown before. Your velocity is going to be tangential to your circular path, and it's going to have a magnitude, your velocity is going to have a magnitude of r omega, where omega is just the angular velocity that this object is swinging around. right? That's from circular motion. I won't cover it in this particular video. I might put a link in the description so that you know what I'm talking about. But we can use this now to re-describe what the velocity of A relative to B is. Well, we know because B is fixed right here, because B isn't moving at this particular point. B isn't moving, and we've only got our net velocity, which is VA minus VB, which is perpendicular to our radius, means that this thing must be swooping out a circular arc. And let me draw that right here to make that a little bit clearer. This is the circular arc point A is swooping out at this instant, right? So that means that this is purely circular motion in this case. This is purely circular motion, right? Which means that it's just rotating around B. I hope that makes sense. So let me just say that I can describe this as both undergoing translational movement and also rotational movement. Okay, and the beauty of splitting this into both just translational and just rotational movement is we can write this as the velocity of A relative to B is now equal to the distance from A to B. Remember, this is B and this is A. The distance from A to B, which is just going to be, well, I'll just call it AB, right? Times by your angular velocity. And in this particular case, your angular velocity will be in the counterclockwise direction, right? But it doesn't have to be. But that's going to be crucial now. So that's absolutely crucial for understanding how to apply relative velocity to solve simple dynamics problems. Okay guys, that's this video sorted. I've got a small little animation that might make this whole concept a little bit clearer. So let's watch it. So right now we've got point B with a velocity of VB, and we've got point A with a velocity of VA in green. Okay? Notice that the movement they do is quite convoluted, right? It's rotating and it's moving at the same time. So what we've done is we've split it into two types of movement. We've got the translational movement, which is this one, plus the rotational movement, which is this. Okay, I'm just going to play that a few more times so you understand it. But I might also put a small link in the description just in case you've got nothing better to do on a Saturday night than watch this video. Alright guys, I hope that makes sense. I'm just going to play it one more time so you get it, and I'll probably do a few more example problems afterwards. Let's just play it out. The end.